In this video, we're going to demonstrate principal component analysis with a very simple example. And for this, we're going to use both Excel and R because it will be easier to understand, because sometimes I can explain it better in Excel, sometimes with R. You don't need Excel for this, but it sometimes is just kind of easy to understand if we can visualize it using that tool. But we're going to start off with this data set right here. And it's a real simple data set, only has 2 points. Now, principal component can handle any number of variables, not just 2, but it's easy for humans to understand 2 dimensions. So we're all going to have 2 variables here. So what we'll first do is read that same data set into R. So let's do that. And if I were to type df, you can see this is the same data set that has been read into Excel. Now let's graph these guys. So if I graph this using Excel, this is what it looks like right here. Now I'm going to graph it using R. So I'm going to plot dfx and dfy, and we're going to put it on a scale of -1 to 12. And there we go. So if we look at both of them simultaneously, you can see this is the same data set. So I'm graphing this. Now, before we go and create principal components, one of the things you're going to want to do is you're going to want to standardize the data set. And when we standardize the data set, what we are going to do is we are going to put things into a scale of between plus and -3. It might be plus and -2 or plus and -1.5, but it's going to be in a smaller range. One of the nice features about that is that if we are dealing with different variables that are on different scales, if we don't standardize, what will happen is that the principal components will give too much weight to the big variables. For example, let's assume I have age and income, and age is like 50 years old and a person makes $100,000 a year. Well, 100,000 is such a big number, it will overpower the analysis. So what we need to do is put everybody on the same scale. Lots of ways to do it, but one of the most popular ways and effective ways is standardization. What do you do in standardization? You subtract out the mean and you divide by the standard deviation. Let's take a look. So here is our data set here. And if we come down here, we could calculate the mean of x and the mean of y, and the standard deviation of x and the standard deviation of y. Let's do the same thing in R right now. So for R, it's dfx, so that's our x variable, and we're going to calculate the mean. And the standard deviation of x is right here, and we're going to store that in mx and sx. And we're going to do the same thing for y. So let's do that real fast. And if I type mx, sx, my, sy, let's take a look. If we bring up our Excel spreadsheet, you can see that our mean, our average of x is 5127. 5127. Standard deviation of x, 3001274. 3001274. The average of y, 5164. 5164. Standard deviation, 307. 9568. So there you go. Now, how do we calculate the standardized version? Well, they are, you take the original variable, in this case 8, and we subtract out the mean, And when we subtract out the average, we're now centering it at 0. So we're subtracting the average, and we divide by the standard deviation. So what were those? Well, that was down here, this and this. We subtract this guy from everybody and divide by this guy for everybody. For y, we do that and that. So when we are done, we will have this 8 gets turned to that number. This guy, 8.6, gets turned to that number. And we do that to everybody. And when we graph it, you'll notice that the shape stays the same, but the scale is smaller. So originally we had this guy from -1 to 11, and now it looks exactly the same, only now it's between -2 and +2 and +2 and -2. So you can see these guys are about the same. But I mean, they're different scale, but it looks the same. Let's do the same thing in R. So we've calculated here, standardized version of X. We take the original X, we subtract out the mean, we divide by the standard deviation. Now, we don't have to do this for principal components because it's going to get done for us automatically, but I want you to understand what's going on. So here we have this guy, and here we have this guy. So we've already run this code right there. Now, let us take a look at the data. This is what it originally looked like between 0 and 12. Now, when we standardize the data and we keep it on the same scale, take a look at this. Boom. It's the same shape, only it gets squished down. And that's what standardizing is doing. It's putting everything on the same scale, and it's a small scale. But this is hard to visualize. So let's put this guy on the scale of plus and minus 2. So that's what this command here is. Let's make the x and the y on a plus and minus 2. Let's do that. So if we change the scale of this guy, there. Now it looks, you'll notice it's centered at 0. And it's between -2 and +2, -2 and +2. And let's take a look at the original data set again. So the original data set looked like this. And when we look at the standardized data, it's going to look exactly the same, only now it's on a different scale. Boom. Okay, not a problem. And we can do the same thing over here with our original data, and here's our standard data. Now let's do principal component analysis. Now the principal component analysis is just going to use our original data, X and Y. So that's what this guy is, say, I want you to do principal component and we're going to only use column 1 and column 2. Well, what was column 1 and column 2? Let's just do that. Head DF. Column 1 is this guy, column 2 is this guy. So we're going to do principal component analysis of this guy. We're going to center it. We're saying center it at 0. And we're going to scale it. In other words, we're telling principal component analysis, we want to calculate this value. The thing we did by hand, principal component analysis is going to do it for us. Okay, and what we're going to do is it will also give us a scree plot. Now we're not going to use the scree plot for this one today because there's only 2 variables and it's not telling us a heck of a lot of information. It is telling us that this guy right here has 2 variables worth of information, the first principal component. The second one has a little bit more than 0. So we can probably get by with just using 1. We're not worrying about that right now. But the point is, we now have principal component analysis done. Print com, here's our variable, center it at 0, scale it. and we put the answer in PCA. If I type in PCA, then it's telling us what the mathematical formula is to calculate PC1 and what's the mathematical formula to calculate PC2. Now we're going to go over here to our friend Excel, and we're going to do that by hand. So principal component 1 is going to be this guy right here, the standardized version. R is doing this for us automatically, but we want to show you what's going on. So we got this guy right here, and it says multiply this guy right here times negative 0.707 blah, blah, blah. And then subtract this guy times the same, in this case, it's the same number. And that's what we get. This guy times him plus this guy times this guy. And that's our first principal component analysis. Our second principal component analysis is this guy times positive plus this guy times, well, it's actually subtracted. Let's keep it consistent here. Wait a minute. Plus negative. It's the same thing, of course, but just want to keep it so that you understand. So I want to do that. Let's just take that one all the way down. Shouldn't answer it. Shouldn't change a thing. There it is. Didn't change a thing. But so what we're doing is we're saying principal component 2 is this guy times minus, oh, I'm sorry. This guy is him times plus 7 plus this guy times minus 0.7. So these are our two principal components. Now, what did we just do here? Well, let's take a quick look one more time at our standardized data. Now, if you notice, our standardized data, most of the information or most of the variation is on this axis right here. So let's put a red line there. Now, what the principal component analysis will do is we're going to make that big red line is going to be our first principal component. So we're going to also make that our axis now. So if you tilt your head a little bit to the left, it would look like a flat line, but it's hard to do that. So we're just going to twist the data ourselves. Boom. So you see, it's the same line, only we're twisting it. So let's do that same thing in R. So here is our original data. So now here's our standardized data. And now we're going to twist that guy. See, now we're going to principal component 1, principal component 2. And it's going to be the same data, only now it's twisted. Boom. See? Let's do that one more time. That's what it was. And now we twist it. Boom. It's the same data, just twisted. Now, here's the interesting thing about principal component analysis is you can see that most of the information is right here on this first principal component. Not much on the second one. In other words, what if I were only using principal component analysis to talk about this point right here? Well, what if I just use the first principal component? I would be able to go right here, and I would be only a little bit wrong. I would say, well, if I just use principal component 1 and go out here, and I don't care about principal component 2, I could just say, let's go out this far, and instead of this being the true point, I can have a pretty good approximation just using one variable. And that's what we're going to do here. So let's do the same thing here. Let's plot, instead of this guy right here, let's plot right there. You can see that we can go from this to this. In other words, we are only having a little bit of error. So if we have like this point right here, if I wanted to go and describe this point, I could describe it perfectly by going principal component 1 and then principal component 2. And it goes all the way here and a little bit up. But what if I don't care about principal component 2 and I only care about principal component 1? I can get a pretty good guesstimate of that data point. And that's the beauty of principal components. I can use less variables. Now, before I end this, the question is, you're saying, well, wait a minute, Don. If I have principal component 1 and principal component 2, and they are both made up of X and Y, how am I getting anything? Well, the reason why that this is important is because think about this as like food, okay? You could say something like, what if I were to say, I'm showing you how to make pizza, and you've got, some bread, and you've got tomato sauce, and you've got onions and pepperoni, and you've got, green peppers and all that. You could say, well, wait a minute, and you put that in the oven and you heat it up and it tastes really good. And you got cheese. You could say, well, wait a minute. Why do I care? Can't I just eat a whole loaf of bread and then eat a whole loaf of a big giant chunk of cheese and a big giant green pepper and eat some tomatoes and then have a whole big, bite of pepperoni, a big pepperoni sausage? I could get the same effect as eating a pizza. I was like, well, yes, you can, but you could cut the tomato up and throw away the parts you don't want, and then you can just use that as tomato sauce, and you can have, slice the bread and only use the bread you need, take some slices of cheese and put that on that. And in other words, you could take the components of the pizza and you can put it all together into one piece of food, and it's better. You don't have to use all of it. We're only using some of it. So that's what we're going to do with principal component. Now we're going to do the same thing, and we're going to use real data next. But this is giving you a good idea of what's going on.